Welcome to the lecture series on deep learning techniques in medicine, where we are covering the module 1 for Introduction to Deep Learning. I am Dr. Shivaranjani, Assistant Professor in the Department of Biomedical Engineering, SRMIST, Kattangalattur. In this video, we will be seeing about the training, the validation and the test set splits and how these are done, and the hyperparameter tuning and the deep learning libraries which are available and used widely. Moving on to the video, we have the three different sets called the training set, the test set and the hyperparameters. The validation set. So what are the training, test and the validation sets? Before going into it, we shall consider a small example. So if a student is going for or preparing for an examination, say. So in that case, if the student is learning, then it becomes the training set. And if the student wants to implement that learning to a practice exam before the major examination, he or she wants to practice that learning in a form of a practice exam or a practical exam, something practice just as a previous go through. If that is the case, then it becomes the validation set. And what is a test set? A test set is the main exam or the university exam that the student writes. Okay, so the learning, the practice exam and the the university exam becomes the training, the validation and the test set. So moving on, what is training set? The training set is the portion of the data used to learn the model parameter. So in the example I quoted, we came to know that it is the learning that the student does for the sake of preparation of the examination, right? So here in neural networks, this is the portion of data that is used to learn the model parameters. So in the training set, this largest portion of the data set is the one which it occupies, which directly influences the model learning. So the model weights are updated using forward propagation and the loss computation, the backward propagation and the gradient descent. So this is how the a network is trained, right from the input to the output, and then how the prediction is done and validated along with the target label, right? So it does a forward propagation, loss is computed. When the loss is known, it goes back again, redirects or recomputes the weights, and then the gradient descent, how much weight should be changed, and then the output is computed. Output or the classification task or the regression task is done, right? So the role of the training set is to learn the weights and the bias, which we give along with the inputs, right? So here it minimizes the training loss and it is exposed to the model multiple times in the sense at different epochs. So you'll see what is this epoch when we are covering the hyperparameter tuning portion, right? So it is exposed to the model multiple times, and the main target of this training set and how this choice is done is to minimize the training loss. Okay. So after the training set, we have the validation set. This validation set, which we call, or the input, entire raw data input is split, right? So this validation set of the input is used to tune the hyperparameters and not used for weight updates. Okay, so we have the hyperparameter tuning that is done at the initial stage. Okay, at the initial stage before the network learns or starts the training. So this validation set is used to tune the hyperparameters and not used for weight updates. Based on the validation set output, we used to tune the hyperparameters. So you'll see in detail what these hyperparameters are and how they should be chosen. Okay. So this is evaluated during training but excluded from learning. When the learning phase happens with the training set, this validation set will stay separately in a folded folded manner. Okay, so they call it as cross validation or five-fold validation, such that. Okay, there are different methods how to keep this validation set separate. Okay, the validation set helps decide how the model should learn. Okay, so how it should learn about the parameters or the input data or the features that is required for the intended task. So we need a validation set to select the learning rate, number of layers, number of neurons, regularization parameters, and to detect overfitting. Okay. So all these, the validation set, the performance of this validation set is used to tune these hyperparameters. These are the hyperparameters that we'll be seeing, right? So it is very important that this validation set performance is required to tune the learning rate. So when you change the learning rate, what happens? So if the loss is decreased or not, right? So this validation set plays an important role. The last point, to detect overfitting. Okay, what is this overfitting? We have heard about this word many number of times when we come across deep learning architectures. They always say the model is overfitting. Okay, what is this overfitting is whenever the training happens, instead of learning the parameters, instead of learning the features, what the model does is like it goes in a raster way and tries to memorize the patterns. Okay, it tries to memorize the patterns, to memorize the features, so that the model comes to a point that it is overfitted. Okay, it stops the training and then it goes to some extent. Okay, right? It stops the training entirely. Instead, it starts to memorize because it is not able to understand what the features are for the classification. So the validation set monitors generalization when the training happens. Generalization, when thus a good generalization happens. So if you are having a training set and a validation set, when the training happens, you will have a loss accommodated along with the training, right? When the model initially starts to learn the data, learn the entire data which is given, then the loss will be very higher in the initial steps. And when the model tries to learn more and more features from the data which you give, what happens is like the training loss comes to a greater extent, right? It goes down, the curve goes down. Similarly, when the validation set is given to the network, so whatever the model has trained and learned, that will be implied over the validation set, right? So the validation loss should also come down. When the training loss goes down in a good way, the validation set should also have a loss going down in a good way. Take for granted if the if the training's loss is going down to a very low level, that it is very negligible. Okay, but the validation loss is not that much equivalent to the training loss, then the generalization doesn't happen, and that is where overfitting comes into picture. Okay, so what happens is like the validation loss goes on increasing while the training loss goes on decreasing, right? That is not a good generalization. When the validation loss and the training loss are decreasing monotonically, when the same happens, then it becomes a good generalization. So this generalization is monitored by the validation set. So how does it help us? So it helps us to decide when to stop the training. Okay, so that is what is called as early stopping. This is one of the important factors that you should note. Early stopping is the one which tells the person who is using the model to understand, okay, my system is not learning that much good and it is not able to detect the patterns whichever that is required for me. So it is better to stop the training. That is what is called as early stopping. and when it should be detected and how it should be detected is decided by the validation set. Okay, so it also tells you like which model configuration is the best. Okay, which model configuration gives you the best result is decided by the validations, gives you a decision through the validation set. Okay, so next one will be the test set. This is the most important one. So the decision on the test set is used only once to evaluate the final trained model. Okay, it is never used during the training or tuning or the validation phase. Okay, so it is an unbiased estimate of the model performance, right? So it also measures real world generalization. Real world generalization is done through the test set. Okay, real world generalization in the sense, as I quoted already an example where a student tries to prepare for an examination. He doesn't know what kind of questions will come in the question paper. All he has done is to learn whatever he has been taught. Okay, he learns it and he does a practice examination for it. But when he goes for a real examination, he doesn't know how the pattern will be or how hard the questions will be. Nothing is known to the student. The same way, the test set is a one which measures the real world generalization of the entire model. How well the model will run for different examples. Okay, so this test set is used after the training is complete, all the hyperparameters are finalized, and the entire model is ready to predict something. Okay, so you give the data from outside, which is not even used or not even seen by the validation and the test set, something that is outside, an X data, which is completely totally out of focus for the validation and training set is given, that becomes the test set. Okay, one important point that we have to note is never tune the hyperparameters using the test set. So hyperparameter tuning, everything should be done. Whatever learning rate, or if you want to keep whatever hyperparameters are there, we should tune it before the test set is given to the model. Okay, so what happens if we are giving the test set before the hyperparameter tuning? It causes data leakage and over optimistic performance estimates. Right? So over optimistic performance estimates will make the system to understand or to believe itself that it knows everything. Right? So that should not be done. So a major question that comes to your mind when thinking about this validation, the training and the test set. How much should I accommodate in each set? How much data should I accommodate? If your data is like 100%, then 70% of the data should be given for the training set and 20% can be allocated for the validation set and 10% of the data can be used for the test set. While the training is happening, the training set can be given, and while the validation phase comes into picture after the training, the validation can be given. Okay, this goes on a rotative way. Okay, and then based upon the validation set performance, you tune the hyperparameters, then again do the training, and then again try to stabilize the model and give a good generalization capacity, which says that as your training loss goes down, your validation loss also goes down. Okay. After that, you give this test set, which is only 10% of data, which is not even seen by the training and the validation set. Right. So, on a brief note, we came to know that what should be the validation set, what is a training set, and how much data should be given in each and every category. Now we have seen that each and every point requires the hyperparameters, okay, tuning of the hyperparameter, which is major in the validation set. What are these hyperparameters? These hyperparameters are the ones that control the design and training process of the neural network. They are not learned from the data using backpropagation. They are set before the training begins. Okay, so we have seen people quoting on two jargons, which is like model parameters and the hyperparameters, right? So model parameters are totally different from hyperparameters. Okay, so what are these model parameters? Are the ones which are learned, okay, ones which are learned by the system. For example, if we have the weights and the bias, they are learned through backpropagation algorithm. The weights are changed through backpropagation algorithm. The forward pass goes on, and each and every time the loss is computed, the weights are updated accordingly, that the loss gets reduced, right? That is called backpropagation. And these parameters are the ones which are learned. They are not set. Okay. Are the hyperparameters learned? No. We are setting the hyperparameters according to the performance that you got in the validation set, right? So they are set before the training phase happens at each and every stage. Okay. So we have seen that the model parameters examples are the weights and the bias, and they are optimized during the training. They change during the training. But here in hyperparameters, they are manually done, or they are being tuned accordingly. Okay. So what are the examples of hyperparameters? Learning rate, regularization weight, the number of layers, number of neurons, batch size, and they are chosen manually or through tuning. Right. So what are the different hyperparameters that are required, or the major hyperparameters that are required in deep learning? First one is the learning rate. Okay. The learning rate, it is a step size for the weight updates during the gradient descent. Step size for the weight updates. What do I mean by the step size by the weight updates? This step size is nothing but how much how much level the weight should change. Okay, if the weight initially was 0.1, okay, so and the changed weight is 0.001. What is the difference? That difference, how much difference should I give? That will be the learning rate, right? The step size for weight updates during the gradient descent, the change in the weights. How much step size should I increase? Should I increase higher or should I increase it lower? Okay, how much? Then comes the batch size. Batch size is nothing but number of training examples processed before one weight update. Okay, I'm repeating it again. Number of training samples that are processed before one weight update. Okay, so what becomes the number of epochs? The next one becomes the number of epochs. What is an epoch? Is the number of times the entire training set passes through the network. The entire training set passes through the network. How many number of times the entire training set passes through the network becomes the epochs. So optimizer is nothing but how the weights are updated using the gradient, the algorithm, the algorithm that is used to determine how the weights are updated. How should the weights be updated using the gradients. We have different optimizer methods called as stochastic gradient descent optimizers, ADAM, and RMS prop. We have different optimizers which we'll be covering in the future lectures. Next one is the activation function. We have seen in the previous video like what these activation functions are, why it is required, and how the types of activation functions such as sigmoidal, tanh, and ReLU activation function, the final output activation function called as softmax, or these. Okay, so it introduces non-linearity on a one-line word, right? So next one will be the loss function. So loss function is the one which tells you like how much your intended output, I mean the targeted output, how much it differs from the output that you have predicted. Okay, this loss function will give you. And weight initialization, there are different the weight initialization methods which can be used. Okay, you initialize the weight and then you multiply it with the input and calculate the weighted sum. Okay, so the dropout rate is like nothing but when you have a large number of neurons, how many number of neurons you need and how many number you need to drop out so that your generalization capacity of the network becomes very good. Okay, we will see about the dropout, regularization strength and decay rate in the future lectures. Okay, we have seen like how the hyperparameters help in generalization, why these hyperparameters need to be tuned, and what are the hyperparameters that are given. So another one important question will be how these hyperparameters are selected. What should or what gives me like which hyperparameter I should choose and which hyperparameter I should increase or decrease. Okay, this is given by the different methods, right? So this is given by the grid search and the random search. Okay, these are the two hyperparameter selection techniques. Okay, so what is this grid search? Grid search is nothing but it defines a set of values for each hyperparameter. It's like a grid. Okay, so this is the important parameter and the unimportant parameter. Any type of parameters. Okay, so if you are giving an important parameter, how much should be the change in the unimportant parameter? It tests all the possible combination, selects the combination with best validation performance. It goes on changing based upon the validation performance. The values of the hyperparameters goes on changing based upon all combinations. So how can we understand it with an example? For example, we have a learning rate. Three different learning rates are there. Which learning rate should be chosen? And the regularization parameter, where there are two regularization parameters. Which should I choose? If I'm choosing a regularization parameter of 0.001, what learning rate should be there? Or if I'm choosing different regularization parameter, what learning rate should be there? That is decided by this grid search. How does it decide? It gives you a random combination. So if you are having the first learning rate and the regularization, that becomes one combo. And the next learning rate and the next regularization becomes another combo. Similarly, the third and the fourth. So how many number of combinations you can give? The total trans becomes 3 into 2, which becomes 6. Okay, now the number of values are very lesser. So the grid search seems to be easy. But when the number of experiments grows, then we have more number of problems with grid search. So if you are having like 5 hyperparameters and 10 values, 5 different hyperparameters and like the learning rate, regularization, dropout, decay rate, or we have the optimization or techniques or different. Okay, so different, and each one has 10 values. You have 10 learning rates, 10 different regularization values, 10 different dropout values. Okay, for all the 5 hyperparameters and 10 different values. So that becomes 10 power 5, which becomes like 1 lakh rounds. Okay, so as the number of experiment grows exponentially, it tends to overfitting. Okay, it is expensive and it becomes a tedious task. But the advantage of it is like somehow we will reach a guaranteed convergence. Convergence in the sense a proper generalization will be obtained with this grid search. So what can be the other method that can be used for a easier hyperparameter selection? Another one is the random search. So this is the one where the hyperparameters are randomly sampled with predefined ranges. Okay, so we are randomly taking some values with predefined ranges. We define some ranges and we take some random samples from the each and every hyperparameter value. If you're having a hyperparameter of learning, we take randomly within a defined range. Okay, which is often more efficient than the grid search. Okay, So here, not all the hyperparameters are equally important, and this random sampling explores more useful combinations. Somehow or other, we have a better combination that is running. So the values are very random, and the output is also with a good performance. The fewer runs are needed for good performance. Okay. So another important point which I want to stress here is that hyperparameters should not be tuned on training data, since it leads to overfitting and poor generalization on unseen data. This most of the researchers or people who are working on deep learning models try to miss it, right? So the hyperparameters should not be tuned on the training set, since it leads to overfitting and poor generalization on unseen data, which is the test data. So on the whole, which we combine, we say that the hyperparameters determine how well a model tries to learn the features. Moving on to the next section, which is deep learning libraries. What are these deep learning libraries? Okay, so you imagine writing every mathematical equation manually. Okay, you are trying to write a mathematical equation manually, and you have thousands of matrix multiplication, millions of gradients, and you go on multiplying, you go on calculating. Is it possible? No, it is not practically possible. It becomes an impossible task. So what can we do? We cannot go on writing. You cannot go on keep writing the codes for the deep learning models. It goes on pages, and so much of mathematical involvement and so much of computational involvement is there. So in order to solve all these, in order to simplify these, we have the deep learning libraries. So these deep learning libraries provide software frameworks. They provide frameworks. Framework is like a predefined or pre-built model network, or um, pre-built software which gives you all the things which you have to do it manually. That simplifies your design, training, optimization, and deployment of neural networks, and the deployment of the deep neural networks by abstracting low-level mathematical operations. So they already have a predefined level of mathematical operations into their framework, and that framework you can use it and make your job simple. So why the deep learning libraries are used? So we already know neural networks involve matrix operations, gradient computations, backpropagation. These are on when you go for a very huge amount of data, it becomes very tedious. Each and every point you cannot initialize the weight, you cannot change the weight manually, and you cannot do those, right? So that can be made easier. So implementing these from scratch will become error prone and computationally inefficient, which is not possible. So these libraries provide optimized implementations and automatic differentiation with GPU acceleration. Okay. So the graphical processing unit that will give you a better optimized implementation of your work, right? So we know that why these deep learning libraries are used. So what are the deep learning libraries that are available for us to work on? Okay, one of which is the TensorFlow. TensorFlow is an open source deep learning framework that was developed by Google. Okay, its operations are defined as computational graphs. Okay, it works on computational graphs. We have the nodes and the edges, where the nodes represent mathematical operations and the edges represent the tensors, the multi-dimensional arrays which we have. Okay, and the major advantage here is like it supports CPU, GPU, and TPU acceleration. We can either use any one of the modality. Okay, we can use any one of the hardware system, like the CPU, the software system, CPU, GPU, or the TPU we can use. If you have a CPU too into your system, you can use a TensorFlow. If you have a GPU, you can use it. Simple, right? So it is designed for scalability and large scale deployment. Scalability in the sense if you are using it in a production system, then this TensorFlow will be very efficient. So it provides automatic differentiation and efficient memory management where the execution is optimized internally, right? So it is used in large-scale deep learning models, industrial applications, and end-to-end deployment pipelines. People who are well versed in coding, they go for TensorFlow. Okay, so it gives you a optimized result. Okay, it gives you optimized result. And if you are having a very large network and you are having very large data, a huge amount of data, it is better to go for a TensorFlow. But the library structure is a little bit tedious for a beginner to go on. Okay, so if you are well versed in coding, you can straight away go for a TensorFlow deep learning framework, which was developed by Google. So another framework which is a part of the TensorFlow, or you can say a subsystem of a TensorFlow, is the Keras. Okay, this is a high-level neural network API. Okay, so this API is the one. Well, API is the one which is a what to say? It's a kind of interlink between two software systems. So, for example, if you want to check for the weather in a mobile app, so you're going to check check the weather in the mobile app. So, if when you're giving a when you're asking the mobile app question, what is the weather today? So this software from the mobile will go and hit the software of a weather substation, and it tries to get the data from there. Okay, so it tries to get the data from this API will try to get the data from there. So it is interconnecting link between two softwares and tries to get the data. So it is used for, so this Keras API is designed for simplicity and fast experimentation. It is integrated as tf.keras in TensorFlow. If you type in as tf.keras, you'll be able to know what is, right? So Keras often focuses on user friendliness, modularity, and extensibility. So when you are a beginner, you can straight away go for Keras rather than going for a TensorFlow. So they just for the beginners to use it, TensorFlow has modified its work and has given it as Keras. Okay, but there are typical limitations with this Keras when compared with the TensorFlow 2. So what are the key features are simple and readable syntax. The syntax is not so complex as in TensorFlow. So the modular components will be the layers where you can change. Okay, so the layers, the models, and the optimizers, different optimizers are in the Keras framework, and different loss functions. Okay, so you have you can do an easy switching between the models and the architecture. Okay, different types of APIs are there. So it is a sequential API and a functional API. So it uses both. There are different types, and that is the sequential API and the functional API. What is the sequential API is, we have a linear stack of layers. Okay, we have a linear stack of layers, and each layer will be one above the other. The difference cannot be there. Okay, the functional API is a more complex structure, multiple inputs and outputs. We have multiple inputs and output. So when the functionality becomes very higher, we go for a functional API. Okay, so the typical use cases are for educational purpose, since I told you, like beginners too can use Keras. And we have rapid prototyping, and we have standard deep learning models. The standard deep learning models that are used for the beginners are available in the Keras. And next deep learning library is the PyTorch. What this PyTorch is, it is a kind of open source deep learning framework that was developed by Meta, Facebook. Okay, this Facebook was the one which developed PyTorch, and it uses a dynamic computation graph, while a TensorFlow uses a static computation graph. This PyTorch will be using a dynamic computation graph. What is the static and what is this dynamic? Okay, so whenever the computation graph is built during the runtime on the go, when the use cases are written on the go, you do a you try to convert into a computation graph that becomes a dynamic. You change it accordingly so that each and every time if you have a bug, you can fix it and then you can try it. But in a TensorFlow, it will be like the compilation should be done and then the execution should be done. Entire thing should be done, and only then you will be able to understand, or you'll be able to debug the system if any errors comes. Here, while writing the code itself, you will be able to test it each and every stage so that you can debug and see, okay, this is where my error gives out. This is where my model is getting stuck. Okay, so there that alleviation is there in the PyTorch. So it allows flexible model design and it allows custom training loops. Right? So the key characteristics are defined by run approach, highly intuitive and Pythonic. Right? So it is easy for debugging. As I told, all these points we have already discussed while telling about the dynamic computation graphs. And it gives a strong support for research-oriented models. People who want to do any kind of research or experimentation, okay, so they can go for a PyTorch deep learning framework. Within the PyTorch deep learning framework, we will be able to give our data, have a pre-trained model, or we can use the pre-trained weights too, or we can design our own model too with this PyTorch. Okay. So these are having novel deep learning architectures within the framework, and they will be also used in academic projects, right? So we have covered all these topics on training, validation and test set, which is the learning, practice and the final examination accordingly. So, and then we saw about the hyperparameters and how well they control the model and how well the model learns all these, the hyperparameters tells. And we learned about the libraries that need some minimal manual math or minimal human intervention to do a deep learning or to do a deep learning task, okay, which is suited for different use cases and all. Okay, so so for PyTorch we go for industrial deployment, and using PyTorch we go for industrial deployment. Using TensorFlow we go for industrial deployment. Using PyTorch we go we try to do research work, novel architectures we learn, and using a Keras we do a beginner's job. Okay. In the next video, we will be trying to cover how these can be used for the implementation of a deep learning model. Thank you.